have any questions about Open Data Science Conference, please reach out to myself or to Hannah Clausen, who will be seated in the back. I'd like to start off by asking about our volunteers who are in the audience, either people who signed up ahead of time to volunteer, or people who are just comfortable helping others get set up with IPython or other things they need to follow along. So if you're comfortable helping others, please raise your hand. And I think just like we started in the morning, if we just start off with kind of a quick afternoon stretch. If everyone wants to just stand up for a moment, you can all just stand up, put your hands above your head. Give it a good stretch for a moment or two. Put your hands down, turn to your right. Well, half of you turn to your right, and the other half turn to your left, and please greet your neighbor. Say hello to someone. Awesome. So everyone's made a new friend now. That is fantastic. If you'll take your seats, I'd like to start by thanking our amazing host. We really couldn't do this without the Microsoft Reactor space, who's hosting us all weekend. We're really grateful for that, and I'd like to ask Libby from Microsoft Reactor to say a few words.
Hey everyone, I'm Libby Erickson. I'm a developer evangelist with Microsoft, and I actually work out of this space as of 2 weeks ago when we officially opened. We're really excited to have a great developer community space here available, and that you all are here today with us. So thank you all for coming out. If you have any questions, I or one of my coworkers will be in the back of the room over there, and feel free to come by and chat.
Thank you. So could we get a quick round of applause for Microsoft Reactor? Well, you know almost everybody here is registered for the Data Science Conference, November 14th and 15th. But again, if you're not, please speak to Hannah and myself about that, or about getting your friends registered. But we're all really excited to see you there. And we're especially excited today to have Don with us. Before I get there, I guess I should say a little before 3 p.m. we'll be having a break for coffee. Coffee will arrive before then, so if you need coffee or tea, that's available in the back of the room. But yeah, please put your hands together for Don to talk to us about predictive analytics.
Thank you very much. Hi. Thanks very much to Microsoft for hosting the event. Thanks very much for Open Data Science Conference for inviting me to come and talk about it today. It's a pleasure and a privilege to be here. So, my name is Don Dini. I'm a principal data scientist at AT&T. A bit about myself. So my background is in computer science and artificial intelligence. Unlike the majority of my colleagues, did not come from CERN, didn't come from the physics lab, didn't come from the finance industry, came from the world of sitting in a subterranean computer lab for solid 36 hours writing code all day long. What I want to talk to you today is about predictive analytics. Very exciting. So just a little bit about what's going to happen. So I'm going to just lecture about some material for about an hour and a half. Then, as I mentioned, there's going to be a break for 30 minutes, and then we're all going to get together and we're going to work on a cool, interesting, real problem. So, predictive analytics. So, what I want to stress first and foremost is that predictive analytics is about solving problems. So what does that mean? So there are a whole lot of companies where there is this initial gold rush, right? Where it's like we are sitting on a tremendous amount of data. Clearly there exists some amount of value in this. We don't really know what that value is, but what we want to do is we want to collect a whole bunch of smart people in an office, and they will figure out what is valuable about our data, and they will help us. So this is not really crucial. The way to think about it is that predictive analytics is about solving problems. Now, when you want to solve, that's an extremely general statement that really only speaks to the general reach of data science in general. So, when you want to solve a problem, ideally, someone has thought long and hard about what is the solution to that problem. Maybe that involves reading a whole bunch of papers and surveying literature and finding that solution, and then you implement that solution. But sometimes the solution is extremely intractable, and maybe nobody knows what the answer is. And really the only way to make progress at that point is to go for a data-based solution. And so actually, I don't know who coined this, who said this phrase, and I absolutely love this phrase, that machine learning is the second best solution to every problem. First solution being the solution. But sometimes we don't know the solution, or we simply cannot make progress. So, I want to give a concrete example. How many people know who this guy is? Very small. Okay, for those of you who did not grow up in the United States during the 90s, allow me to tell you about this gentleman. So this is the Crypt Keeper. The Crypt Keeper is he is a puppet operated by, I think, 9 separate people. He's the host of this horror anthology show on HBO called Tales from the Crypt. Wonderful show. I absolutely adore this show. Highly recommend it to all of you here. Actually, it's very apropos since this Halloween season. I think someone just jacked me from the display. Someone just took the display away. So, the Crypt Keeper. So, at the beginning and the end of every episode, he would just speak and do a little segment. He would do an introduction to an episode. Episode would air, and afterwards he'd be like, he would say something relevant to that episode, sort of in like Rod Serling, Twilight Zone fashion. But think Twilight Zone, but with a horror theme. And the thing that he was really, really known for was making terrible puns. And I have this really great video, it's a clip up from YouTube, which is a montage of his puns to give you an idea. I'll see if this works. Personally, I can only type audio through this mic. We'll see what happens.
Today, we'll be learning about spherical bonding and the right way to look behind when acting up. Hey, you! Watch it! I tell you, kiddies, I'm going to get that guy. Which brings to mind the 2 men in tonight's dinner table. They're on a little shriek and destroy mission of their own.
And so on. Anyway, like I was saying, terrible puns. I think I could watch that. I could watch that indefinitely. It's funnier longer than I listened to it. But maybe that's because it has a warm place in there. So the question is it possible to make a computational pun generator? Let's suppose that I have a goal. I want to do this. I want to have a Crypt Keeper on demand. I just sort of want him to, like, so if he's following me, he's behind my shoulder, and I sort of on command, I can have a pun generator. What kind of progress can we make on this one? So, the Crypt Keeper makes 2 kinds of puns, as it turns out. The first kind of pun is a self-contained pun. So the self-contained pun is, you don't need any knowledge about anything outside of the pun in order to understand what it's about. So, for example, you could say I'm full of holiday fear. So it's very clear that it's sort of taking like the horror-themed word fear and substituting it for cheer. The second kind of pun is one which is a little bit more complex to put together, but it requires knowledge about events outside of the sentence in order to operate. So, for example, I've heard of going out on a limb, but this is ridiculous. So that was right after an episode in which someone had their arm chopped off. So right now, let's talk about the first kind of pun, self-contained puns. So what we would like to be able to do is put in the sort of plain text version of something totally terrifying, and we would like whatever system we create to automatically detect, aha, I could actually use the word scare from scary, and it rhymes with this part of the word terrifying, and I would like to substitute it in there. Is it possible I can write down a set of rules, a set of guidelines to accomplish this? So, it turns out Carnegie Mellon University, they maintain this thing called CMU Dict. It's extremely handy. Some of you may be familiar with it. So it begins a pronunciation dictionary for lost words in the English language. And what they do is they break down words into basic, roughly syllables according to this. So the numerals sort of roughly correspond to which one is considered a primary syllable when it is pronounced. So the EH, the terrifying, is meant to be accented. So what we would like to have happen is we would like for this part of terrifying, right, the terror, we would like for this somehow to automatically recognize that it sounds kind of like scared and scary. You're like, aha, therefore I can make a substitution. So, one evening, I don't know, like several weeks ago, I spent, I don't know, most of the evening trying to come up with a set of rules to perform that substitution. And it turns out the longer that I did that, the more there was exception. There was one exception after another. And then eventually it just became just like ludicrous. It was just not possible to capture something in generality with a question of rules. And I thought, wait a minute, this is why data science exists. This is why machine learning exists. It's because precisely for such a situation, when there are a whole bunch of rules, and the answer is really complicated, what I can do instead is look at many examples where I know what the answer is. I know what the problem is, and I know what the answer is. The question is, can I whittle out some sort of generality? Some sort of generality that's sufficiently useful where I can use it to make progress on this problem. Foils and rules, I love it. So one way in which to make progress on the problem, and let's suppose you have a lot of examples. So what you want is, recall, you have a collection of words. So in this case, we have a collection of like horror kind of themed words, right? So like scare and ghoul and boil and things like that. And we have new sort of like unconverted text. The idea is we want to figure out which word in this sort of horror themed words does a syllable here rhyme with, or is it close to it somehow. So one way to approach this is if you have a new word, like snare, you could define a metric by which it is close to the existing words that you know about. You use that metric to find the existing word that it is closest to. You say, okay, that's the one that I'm going to decide that it is that it rhymes with, and I'm going to do a substitution with that word. And you can see that because of this metric, you're kind of forming this boundary a little bit, right? By which roughly the sound like air, snare, sort of is corresponding to, or like you could do a substitution based on that sound. So of course, I'm sure many of you in the audience have seen this model. It is the K-nearest neighbors model. It's extremely simple and it's extremely effective. Actually, it was one of the best models for doing handwriting recognition until support vector machines came out, which were invented at AT&T, by the way. By Vladimir Putin, who now works at Facebook. So, if you implement the system, without too many examples, you get something like this that comes out of it. You can put in the sort of non-converted text for richer or poorer. And when you get out the other end is for sliver or horror, which I think is pretty good, right? So this is a way in which you can make progress on a problem which is well-defined, but you don't actually know how to solve it. You don't know what the solution is. But simply from having many, many examples of it, you can make progress on the problem. And I think this is a great example of where data science is useful. How can it be useful? It's when you have a well-defined problem which you're trying to solve, but it is for whatever reason intractable. The people who are domain experts, maybe they don't exist any domain experts. And so the only way you can make progress is database definition. This is where I got to talk about examples of this. So there are many, many examples of this in all over science and technology. So a really great example is physics. So in physics, one of the great reasons why so many data scientists come from physics is because you face such problems. For example, in particle physics, You face this problem in which you take a whole bunch of particles and you smash them against each other. You look at what data comes out in a bunch of sensors, and based upon this data, you're trying to figure out what was in this stuff that I smashed together. And so to do that, they use data science. Basically, they look at data that comes from simulations. They use this along with math, analytical tools, and this gives them ideas about probabilistic models and use that to perform inference. So predictive analytics is a very, very, very large field of study. Certainly it's not possible to go from 0 to 0 to practicing just within the context of this workshop. But what I wanted to accomplish today is tell you about a few things which I think are very, very important to keep in mind. And so if you are sort of just getting started with predictive analytics, these are things which I hope that you will keep in mind and will be kind of guiding ideas for you as you continue. So I'm going to go through a bunch of examples. Some of it will involve IPython, and you can follow along everything that I am doing. I have I posted the IPython notebook that I will be working from, as well as all of the data that I'll be using on a link on Dropbox. So you can find that link. I put it on my Twitter channel. So I'm just at Dini, that Dondini, and should be my most recent tweet. So if you go there, you'll find that. Here we go. This is me, Dondini, and this is the top node. There we go. So if you do not already have IPython notebook installed, I suggest that the way that you do that is you go get the Anaconda installation. For people who have volunteered to help other people get them installed, I greatly appreciate it. Okay, so as I was talking about before, predictive analytics is about problem solving. So it's not simply, here's a bunch of data, let's propose a model, let's train it, and then see you later. There's the science part of data science. And so the way that I like to think about that is that the process of solving a problem occurs in the context of this sort of QMV process. Questioning, modeling, and validating your modeling. And it occurs in these iterative loops. So you start with some sort of vaguely defined question. So for example, are my servers being attacked? It's not really quantitative, right? It's hard to sort of take action based upon this. Are my servers being attacked? I don't know. I have to turn this into something in order to make progress with this problem. And in the questioning phase, you start with this vague question, and the goal is to turn this to a very specific statistical inference problem. Now, there are many, many options, but the idea is you want to start with one. You see how it works out. Depending on how it works out, you revisit this question. You say, maybe I phrased this as a hypothesis testing problem, but based upon how it turns out, you know what, it would really be better as a regression problem. But you have to start somewhere. So, this is actually a problem which we face all the time at AT&T. So AT&T is a very, very large company. It's responsible for resolving a very large number of DNS requests for the internet. Sometimes those machines which are serving those requests get bombarded with DDoS attacks. And so there's this problem of, is something really popular simply happening, or are we in fact being attacked? And so this is a problem we are actively doing modeling for. And so one way to turn this into a specific question is an idea as a hypothesis test. I'm going to have a null distribution, which corresponds to some notion of normal, and then I'm going to test deviations. So the next phase is the modeling phase. So the idea is that once I've gotten to the phase where I have a specific statistical inference problem, then I want to come up with a model that addresses that. So this is where you take that question and you say, for example, it's a regression problem. You can address that with the k-nearest neighbors, with linear regression, support vector machines, and so on. And again, you're not stuck with an answer. So the idea is that it's an iterative process. You start with one, you see how it meets the model, you evaluate this model, and then based upon that, you revisit earlier steps until you, and it's this monotonically increasing value process. Lastly, the validation phase, in which you might just evaluate how well does my model work out. And that could involve many methods of performing validation, like simply looking at mean square error or an ROC curve, or trying to evaluate uncertainty confidence. So, for example, here is what that process looks like for a problem that I saw previously. We're actually going to be talking about this later today. So this problem was about trying to understand what are things which influence communication on social media. So the idea is we started at the very beginning with, is it possible to predict the next time that a person will tweet? And what are things which influence this? And we start with some idea of how am I going to turn this into a quantifiable problem. And then all the way to the end of the process, in which you have an answer and you have a model which kind of squeezes all the juice out of the process. So incidentally, this was a model I performed for a blogger. It was a blogger named John Gruber, who I'm sure many of you are familiar with. He has the site Daring Fireball. It turns out he's extremely predictable in when he tweets, and I was able to produce a model that was able to predict when he would tweet within 5 minutes, like 85% of the time. That would freak me out if I was someone over anywhere. So, let's look at an example of this. A very simple problem. I'm receiving a constant list of numbers, and I simply want to predict what is the next number going to be. Right? It's hard to think of what is a more pure version of the prediction problem. So, first thing we want to do is this question, predict the next number, but I want to turn this into a specific statistical inference problem. Right, well, we're trying to predict a number, so it seems very reasonable that we would consider it as a regression, right? There are ways in which you might think of it as a classification problem. But why not start with a regression problem and see what happens? So we have a way to capture it as a problem. Now the question is, how are we going to address it? How are we going to answer that question? So we have a bunch of data points. Let's suppose, we don't know this is true, but it's a hypothesis. Let's suppose that these numbers that we have been sampling are coming from a normal distribution. And so if that's true, the best prediction that we can come up with is just the expectation value of this distribution. And if that's true, then the best estimate of that is the sum of the numbers divided by n. So the question is, how will we figure out how well this has worked out? So one way in which it's important to think about this is we want to think about how sure is this model about something that is recognized. So one way to get a feel for that is confidence intervals. Now, there are a great many analytical expressions for coming up with confidence intervals based upon your models, based upon data that you have seen. Some of them can be extremely interactively difficult to calculate, but you can get around a lot of this by instead using computationally computed functions. And I want to talk a bit about that. So here's the idea. Let's suppose I have some regression function R, and I want to evaluate it at point X. And the question is, how well is it doing? How much uncertainty is there in the output of this? So, an extremely effective way to go about answering this question is something called bootstrapping. So bootstrapping, the idea behind it is you have a very large data set, and you want to simulate many smaller data sets. So, for example, if you have a data set of 10,000 points, you would produce, for example, many smaller data sets of 1,000 points comprised of randomly selected pieces. So in this example, we had a large data set, and we were creating many bootstrapped smaller data sets that are created by randomly selecting items with replacement. Now, for each one of those randomly created data sets, we're going to train our model. And then we're going to ask the question, based upon that new data set, what is our estimate for the value of X? So ideally, if we have a perfect model, and the data that we have is absolutely perfect, it should be like the same, right? It should not vary very much, right? It should basically be like, okay, well, I understand this problem, I have representative data, and it doesn't really matter. Like, I have sort of extracted the necessary juice from this problem. And so we can calculate this, right? So let's just get the collection of values that are estimates for the value of X.
One of those that's like a single dimension array.
So RFX would be, for example, so as I'm going to show right now, so the question would be like, what's the average value, for example? Let's suppose I have these incoming values and I want to measure what's the average of these of the distribution. So what's like the mean of the normal distribution that these numbers have been sampled from. And so RFX would be the mean of that distribution. Right, so I've sampled like 100 points.
Okay.
What's the mean of the distribution that produced these numbers? Right, so if I have a good collection of numbers, and it's the same distribution that I'm getting, I should spit out the same answer each time, right?
Sure.
And so the question is, let's investigate if that's true. Okay, so here we have so I believe by default is producing so here it's producing 100. So the data set is 100 data points, and so it's 100 data points and it's producing. A number of bootstrap samples. So the idea is, I believe it's 50 bootstrap samples. And so the question is, okay, so for each one of those, the idea is that it's come from the very same distribution. I'm going to take the mean of these numbers and make a guess as to what is the mean of that distribution. And so, if the data points were perfect, this wouldn't be a histogram, right? It would just be like one bar right in the middle, right? I'm absolutely sure what the mean of this distribution is, right? But of course we're not sure, right? And sort of intuitively this makes sense. If the number of data points we have is small, we're not very sure. And so if we increase the number of data points to 1,000 data points and perform the same process, little bit better, you know, this is sort of eyeball views. But we can gain a sense of this. So the blue in the background is the actual normal distribution that was set to produce these points. We have just 100 points, and I take a bunch of bootstrap samples. This is the 95% confidence interval of those samples. So it took each sample, calculated the mean, and the mean ranged over this entire range. Where, of course, the actual mean is greater. So instead I changed that to, after having 500 points, that changes it a little bit. And then of course if I have 10,000 points, it improves it, right? It's much more, Sunder is a much more accurate representation of what the mean is. Although still, not a single point, right? It's still not one single point right at 0. There's a bar of uncertainty. It's somewhere within this range. And so what I'm trying to communicate is that because of the amount of data that you have present, this inherently introduces some amount of uncertainty in an estimation that you wish to make, that you cannot get rid of. And it's important to communicate it along with your prediction. So if you were going to say, what's the next number I'm going to see? And your guess for that is, well, I think this came from a normal distribution, so my best guess is the mean of that normal distribution. So I'm going to tell you what the mean of that distribution is. However, I can only tell you that the mean is going to be somewhere within this range with 95% probability. It doesn't matter how deep your deep learning network is. It doesn't matter how many trees your random forest has in it. You simply cannot compress it beyond this amount. The data just doesn't support concluding something with greater accuracy than this. So why is that important? What do you think? Why is it important in order to communicate the uncertainty with the prediction that you have produced? What is the concrete use?
You need the more important decisions need less uncertainty. You need to know, in the next 1,000 years whether something's going to blow up 10 times at one time.
Yeah, absolutely. Anybody else?
Yeah, for like online marketing, you can have more uncertainty than you can in, say, like a new medicine.
That's true. Different industries tolerate different amounts of uncertainty. So I'll give you a couple of good examples. So one example, I was talking to the chief security officer for an unnamed, extremely large multinational corporation. And he was telling me about intrusion on his network. So he's sure that intrusions are happening. His team comes to him and says, an intrusion occurred on this day. But he had the intuition to ask, well, what is the uncertainty on that, on when that intrusion occurred? And the answer was, it was plus or minus a week. Right? Because when an intrusion happens, like, there's no like buzzer that goes off. It's like, oh, someone is in your system and like doing something terrible, right? It's like you are looking at a very vast array of logs. A lot of the information is aggregated over a long period of time, and trying to pinpoint exactly when it occurred, like there is uncertainty that happens with it. And because the uncertainty was such a wide margin, that then gave him the knowledge. We need to change the way in which we're collecting our data in order to facilitate saying things with a smaller amount of uncertainty. Another good example I really love talking about. So the cool thing about working at AT&T is you work with like every kind of data. So first thing, so I arrived there, I started working on a problem involving like data centers, which is a really cool problem, by the way. So I was sitting there working on my desk. This dude walked up to me. He works in a facility in Atlanta. He's like, "Hey Don, we need someone to work on predicting when a UVerse technician is going to arrive at someone's house." So it turns out, one of the most frequent calls that AT&T gets, the customer support, is I'm scheduled to have viewers arrive at my house today, like when are they going to get here? And so they're really good, it turns out, at getting you there within like a 4-hour window. But they want to get it within like a 30-minute window if possible. So like at the beginning of the day, or the previous day, like it would be really cool if you could go to the customer and be like, the person's going to be here between this 30-minute window. And they're like, Don, can you work on this problem? And I'm like, yeah, I'm not doing anything. Like, why not? I'll work on that problem. It sounds like fun. So we looked at this problem, and it turns out that there was just too much uncertainty in the data. That you could not say anything within a 30-minute uncertainty range. Everything that you could say was like plus or minus 8 hours or 4 hours. It really just like you couldn't give the management what they were asking for. And it's very important to be able to explain that to whoever is asking you to do anything. That yes, I can give you an answer, but the answer has with it this sort of uncompressible amount of uncertainty. And computational confidence intervals are a really great way to express it. Okay, so that's one source of uncertainty that we talked about, which is not enough data, right? So what are other sources of uncertainty that we have to think about? What should we do about it? So this is a question I talked about earlier. What are things that influence communication on social media, right? This is something that all kinds of people care about for all sorts of different reasons. It's a very vague question, but it's very important. So the question is, how do we turn this into something that is quantifiable, right? How do we turn this into an inference problem? So does anyone have any thoughts about that?
Current events.
I'm sorry?
Current events.
What do you mean?
Are you asking for an answer to the question, or?
Yeah. Well, so the question is, so yeah, we want to answer this question, right? And so if we do the answer, we would give them the answer.
I was sure a factor, I guess some factor will probably be current events, maybe news cycle or current events that are happening. Because most of the time, if something big happens, a lot of people take to social media to express their opinion. So I would think that would be some feature or something to monitor. I would think.
So maybe like frequency with which occurred.
Yeah.
Within like a per hour or something like that.
Maybe so, or if it's, I would depend. I guess if you were looking, say, in politics or something, when a debate happens or something, that would be something you would like to monitor. Or,
Oh, I see. Yeah. Okay.
yeah.
Yeah, absolutely. Okay. Anybody else?
Define a set of things you can test, which can influence, and then test each thing.
I'm sorry. Could you speak more loudly, please?
Define a set of things which you can test, which might influence, and then test each quantitative things against the outcome. And you define what is the communication.
I see. So sort of like an experiment, like experimental design. Does anyone have any other thoughts about how we can quantify this problem? Yes, sir.
Possibly look at what the top influencers are talking about.
Okay.
We look at whether someone has already communicated. That's a good signal.
Could you elaborate on that?
That's it. Communication has already happened within a group. Then the chances of that not communicating again is
I see what you're saying. So the idea is that a thing which influences communication, that communication has already occurred.
Yeah. If it's occurred in the past, we'll be going again.
So we're going to investigate this question a little bit. We're going to use a data set that's in this link that I posted. So there are, so in this data set there are maybe like 2,000 tweets from 3 separate individuals who are friends with each other. So I highly encourage you to investigate all of these questions. So I can tell you what I chose. So what I ended up choosing was, given the elapsed amount of time since the last time a person tweeted, how much longer to go until they tweet again? So I can call that inter-tweet time. The idea is that if we can understand things that are related to this, things which have influence over this, we can gain some kind of understanding That's sort of that's the quantity that I choose. So let's look at this number, inter-tweet time. So on the x-axis here, what we've got is how long it's been since you last tweeted. So I just tweeted, it's been 20 seconds, it's been 40 seconds, and so on. Now, the y-axis is about a 95% bootstrap confidence interval of how long was it until you tweeted next. By the way, this is looking at the same gentleman again, John Gruber, here in Firewall. So sometimes, after 20 seconds, he tweeted immediately. Sometimes, he tweeted after 30,000 seconds. This is a massive range, right? And basically every amount of time after the initial tweet occurred. Right? And so based upon no other information, if we wanted to create an estimator about, so if someone asked you the question, okay, 30 seconds has elapsed, how much longer until they tweet again? We have no additional information. What's the best thing we can say as an answer? Does anyone have an idea? How would we go about getting an answer? So, yes, sir.
I think I'm confused about whether you go top to bottom or bottom to top. So you started talking about that you want to study the communication patterns on the social media. I started thinking, why would you like that? What is it exactly? What's your goal? Or maybe
Why do people want to study that?
yeah, maybe having clearly defined goals will help you go after like certain factors and then deal with this kind of thing.
Sure. So why do you think it might be important to examine that question of like what are things which influence communication?
Well, it depends on where you work on, what's the goal going to study, maybe for marketing, sectors, maybe for communication, enhancing communication to certain segments of the context.
So you're absolutely correct. So I can tell you that so Twitter, because pretty much everything you write there is basically a matter of public record, it's extremely amenable to research, and they're like informal, like journals of Twitter research, basically. So one of the things that people study in particular are things like travel patterns, for example. So there was so a colleague of mine studied this problem of when recently there was the volcano that erupted in Iceland, and it caused all these changes to transportation patterns. There was a large amount of research which was dedicated to trying to understand the problem. How did travel change as a result of this? How is travel impacted by this? And the idea is that people, especially people who are travelers, they use Twitter in order to communicate with each other, in order to communicate like availability of routes, for example. And so that's a particular instance in which people are studying precisely that problem. There's another, so one of the problems that I examined at the office is trying to use Twitter in order to understand how do people talk about events, for example. So for example, Caltrain. Caltrain is one of these things in which people who use it are very frequent Twitter users. And you could ask the question of like, how do people talk about the event of like the train breaking down, or something more mundane like the bike car is full? And you can actually look and see that like there are phrases that people use to talk about these events. This gives you the idea of like, okay, if I want to sort of detect whether or not that has occurred, it'll give me knowledge of like, okay, I can search based upon these phrases, and this will give me like a detector, right? And then a really interesting part of that problem is we discovered that if you go to, this was highly community dependent, right? So if you go to a place like Boston, for example, you know, for exactly the same events, like a bike car being full or something breaking down, they're both English-speaking societies, but they use different words to talk about the same event. And so this entailed like other sub-problems, like community detection and things like that. So you're absolutely correct that the nature of the problem you're trying to study is highly influences how you would go about studying.
Could you first explain the axis? I guess I'll...
Yeah, absolutely. Sorry. So let me talk about that again. So what we're talking about here, so the idea is we're looking at a particular individual, right? we looked at the quantity of how much time is in between successive tweets, the intertweet. So on the axis here, what we're looking at, the x-axis is, given that 20 seconds has elapsed since you last tweeted, how much longer to go until he tweets next?
Okay.
The y-axis is how much longer he has to go. But it's trying to convey the spread in this amount. So sometimes he tweeted again immediately.
Okay.
And sometimes after 20 seconds, you have to wait another 30,000 seconds.
Okay. So this is a confidence interval. This is an interval.
You got it.
Okay.
Exactly. So the idea that this is trying to convey is that there's a huge amount of uncertainty,
Yeah.
right? And so if you were just going to go on this, if someone said like, okay, I know 30 seconds has elapsed, how much longer should I wait? So it turns out the best you can say is an average of the points along this interval. Take the expectation value of this interval. And that's the best answer that you can get. Which kind of sucks, right? It's not that great, right? So if someone said, like, I want an answer to this, like, really what you could say is, I don't know what the answer is, and there isn't really a good way to tell you based upon this model. So what should we do about it? So, we want to figure out if it's related to other things. Do other things impact this? So, to gain some intuition into this, let's suppose y is totally determined by x plus some noise, right? So there's a total linear function happening here, but there's some noise happening on the top and bottom. And so I'm going to perform the same exercise, where I'm going to look at the points that happen at each x value, and I'm going to I'm going to perform the same process. I'm going to look at a 95% confidence interval, and given that x was 20, how often was it a negative 50, and sort of what was the spread at this value of x equals 1? You can see that it was sort of this amount. And you can see that we know what the true model is, and there's really no more you can squeeze it down beyond. The uncertainty is just going to be within this band. But let's suppose that it actually depended upon an additional feature, upon y. But we didn't know this. We were just paying attention to x. So we thought it was simply y equals 2x plus a noise term. But in fact, there was a 2y, which depends on, but we weren't even paying attention to it at all. So this is what happened as a result. That additional y wiggling around shows up as additional variance.
So is this a y value that you're feeding into?
So what I did is I have x, and I know what x is, so I can purposely vary x from 0 to 100.
Okay.
But y takes on a whole bunch of random variables that I have no access to.
Okay.
And so y, I randomly put that in there. And then, of course, there's this noise term, which we carry over from the previous one. The idea is that there's this motion from y, which is impacting y, which is what we're looking at. And it's showing up as making it swing wildly from one side to another. And so, where previously I couldn't squeeze this anymore, right? It's just sort of stuck here. And this next one, if I just knew about y, I could squeeze this, right? I could reduce this amount of uncertainty if I just knew about the existence of y. And so this motivates the entire reason for looking for features. This is why people look for features.
So those two Y's were different. Or were they the same?
Well, I mean, they're the same in terms of what they're both the same domain of values. They simply occupy a larger range of values due to the influence of another variable. Please, yeah,
Well, I'm
go ahead.
confused because, I mean, you said that it's a different feature, so it sounds like something that's being changed that's modifying the output. Like, so Y is the output, right?
That's correct.
So it looks like you're including the output.
I understand what you're saying.
It's fine, but
Yeah, so, yeah, that is a typo.
Okay.
Sorry, this Y, I should have used a different variable.
okay.
Yeah.
Thank you for pointing that out.
I was curious.
That what?
That was an error.
Yeah, okay.
So, this is why we look for people. So how do we look for features, given that we know we should be looking for them? So this is essentially asking the question, I have two variables, x and y. I want to know, do they have something to do with each other? So what's the answer to this question? How do I conventionally figure this out if x and y have something to do with each other?
Correlation.
Correlation. Anybody else? You get a gold star. So both of those answers are correct. So the first one, let's talk about that correlation. Absolutely correct. So in other words, that's normalized covariance. So there's an issue with covariance. So here's the problem. Let's suppose I'm looking at this function y equals x squared. Y is completely determined by x squared. If you were to look at the correlation between x and y over this range, so this is just for a sample of points, but if you were to evaluate the integral of this, the answer is 0. Correlation is 0. Which of course is bad, right? We know y and x have a direct relationship, but it's not revealing it. And so what you will find if you carry out the integrals for different polynomials, you'll see that for all even degree polynomials, square, x to the fourth, and so on, you get the same answer. The correlation is 0. For odd degree polynomials, it's non-zero, but it decreases as the degree. And so correlation is a good tool. It's an important tool, but it's not general enough. We need something to add to this bucket of tools. So to understand what that is, let's talk about information theory. So information theory, we're thinking about the very same thing. We have x and y, and we're trying to think about, are they related to each other? So in order to understand that, let's think first about x, random variable x. Let's suppose that it takes on two possible values, x1 and x2. And so we can think about what is the value of that probability distribution. That thing I value x1 and x2. So you can just go ahead and evaluate this from probability table and get this answer. But let's suppose I knew that y was fixed at y1. Does that matter? And so if y is fixed at y1, and you were trying to evaluate the very same expression of the probability distribution for x, how does that change? You see that it has in fact changed, right, to 0.16 and 0.84. And so it has caused it to skew a little bit to one side, towards x2, right? So the knowledge that y took on the value of y1 mattered. It gave us some useful information. So you can measure the degree to which that occurs, the degree to which knowing the value of one of the other variables tells you something about x. And we measure that using an expression called entropy. So entropy is defined in the following. If you have a random variable x, it takes on a bunch of values, x1 through xk. So those are not data samples, those are the possible values that I can take. And then they occur with a probability distribution described as such. So then the entropy of that random variable is the probability of the value times the log of the probability, and the sum of those, n minus 1 times all of those. That's the definition of entropy. Now, why is that definition useful? So it has very useful properties. So when the probability distribution of x is its most skewed, and yes, I understand in statistics there is in fact a formal definition for skew, which is not this definition, so when it is sort of most certain, right, where all of the values are 0 except for one particular value which are absolutely certain, entropy of the distribution is at its minimum value. And at the very other extreme of the spectrum, when you're maximally uncertain about what value x is going to take on, so all of the values have an equal probability of occurring, entropy has its maximum value. And so this gives us exactly what we want, right? So as the probability distribution becomes more certain, as we go from total spread closer to one value being 1 and the rest being 0, the entropy of that distribution goes down. And so we can examine the relationship between variables by sorting them according to how much they cause the entropy of x to go down. So it turns out that's how decision trees work. So a decision tree, when you're building it, well, according to one of the popular algorithms for building a decision tree, when you're going down the tree and you're deciding which node should I split on next, the way that it decides that is precisely according to this manner. It's asking the question, which variable is going to make me maximally certain about the outcome of the response? So of course, when we want to use this, we want to look at y and take on a bunch of values, right? So if you take on the value y1, and you take on the value y2. So what we want to look at is the expectation of how of the new value of entropy as a result of knowing the value of y. So that expression is called relative entropy. So if we have a collection of variables, A, B, and C, and we're trying to understand what is the relationship of these variables to another variable x, this gives us a way in order to sort them by their influence on x. Right? We take h of x, we compare it to h of x given A, and we examine how much did the entropy go down? How uncertain was I about x after learning about A? Okay, so let's apply that to our problem, right? So what were we trying to do? We had this problem, right, where we're looking at the time between tweets, and we saw that there was this massive spread. And the idea that we're trying to get at is, can we reduce this spread, right, by looking at features? So what might we propose as features to look at? So the data is there for you to play with. You can look at whatever features you feel like looking at. What I looked at was I had a hypothesis that precisely what this gentleman said, that if people in his group spoke recently, that would have an influence on this person's speaking. So I refer to that quantity as mention distance. The idea is that the number of seconds that have elapsed since someone in his friend group has spoken. And I chose two particular people in this group. I chose John Siracusa and Marco Armand, the people in the same community. And so those data sets are in the package as well. So I looked at a number of seconds since either of them at mentioned this person. And other features I looked at is time of day, does it contain a mention or not, does it contain a URL, length of the tweet, whether or not it contains hashtags, and is this a reply or not. So all of these are variables to consider, and we want to examine, do they have a relationship with this other variable, which is intertweet? And we can do that using this tool of information. So this is a bunch of code about just about forming these features.
So the Twitter tools, are those packages that you created, or are those part of Python?
I created them, and they're in the package. So here's where we create for each tweet, we try to figure out how long has it been since either John Siracusa or Mark Armand mentioned them. Just trying to extract the features. Okay, so time of day. to evaluate the entropy of X, and then the entropy of X given Y, and then the difference between those two. So it's just this number, relatively small number, contains mention, another relatively small number, contains URL. So this library of information game is also in the code that I distributed, so you can feel free to use it if you like, or use another tool. There are other libraries that are out there about calculating information game, but I think for the most part they are for the continuous value variety. But feel free to look. So length of it, let's look at what are the difference in measures. So a very large value, 3.18, right? So this says, the other, relative to the other value, right, it's like 1,000 times more influential, right? So it turns out that if I know the length of the tweet, if I condition upon this, it leaves me the least uncertain about how long it's going to be until he tweets again. Which kind of makes sense. I guess you can sort of convince yourself that that's true. Contains action. Not very much. Digital also not very much. Here we are, mention distance. So this was the hypothesis, right? So here's the idea that if I know how long it has been since someone in this friend network has mentioned him, does that have an influence on how long this person tweets? And the answer is yes, right? It's another extremely large net. Intuitively, this makes some sense, right? So essentially the idea is, if I call your name, I'm like, hey, so-and-so, you are likely to respond to me. And it's this discontinuous jump, right? So it's not one of these things which is gradually varied, whereas one thing varies, another thing varies along with it. It's this total, like, discontinuous event, where, like, I call you, you immediately respond. And so in order to capture this, and things like this, it's very challenging to use a tool such as covariance. And it turns out that a phenomenon like this happens a lot in networks of information.
So this entropy loss is 2 point. Is there any interval that we're expecting for the entropy loss value? Because I saw most of them were a little bit smaller. I didn't know it was between like 0 and 1.
That's right.
Okay.
Yeah, yes, so the question is like,
is there an interval? Is it like probability like it's going to be between 0 and 1 in a sense? The entropy loss of value?
yes, the question is how do we interpret the meaning of this?
Yes.
Right? So, so the units of the number, if it's in the logarithms or base 2, they call them bits, but you know that's just a name. Really the way to go about this is through comparison of how does this compare to another value, right? So if they were all like a relatively small value, or if it differed from another value by a very small margin, you know, then the answer is like, well, it doesn't really seem like there's much of a relationship.
Okay.
Actually, that's a very good point. So this is one of the reasons why you include spurious variables. So let me give you an example. So I entered a class along with my coworker for ODSC, a class called Model Building and Validation. I'm going to talk about this problem in a little bit more depth. But we started the class off with this problem, which I thought was cool, which I would ask actually in interviews a lot, which was, let's suppose you have a candy bowl up, sitting out there, and has a whole bunch of candy in it. And let's suppose you were able to just sort of view what people chose, and you sort of knew like attributes about them. Like you observed like their age, maybe their hometown, or where they sat in the office, people they sat by. And like, what would you do with this? Like, what interesting questions could you ask? What might you conclude from this? And the response I got from UDSC was like, who cares? Why does someone want to know about that? I'm like, well, because it's cool. I think it's interesting. But anyway, so in trying to answer this question of like what influences essentially what will be chosen, we we included a spurious variable. So that was shirt color, right? This is one of these things where you know shirt color should have nothing to do with this, right? Shirt color does not influence what sort of again you select. And so if something is sort of ranked beneath shirt color in terms of influence, if you were to do this information gain analysis, and something was valued less than shirt color, you know you can ignore that, right? You know, like, okay, it doesn't matter. And that sort of gives you this knowledge of how to calibrate what number value you should pay attention to. Okay, so what do we get out of this? So we got two features that seem to have a big influence. The length of the tweet and mention distance. So the idea is that we want to use this to squeeze this amount of uncertainty. Can we use this information in order to make it small? The answer is yes. Let's do that. Okay, so I did a 10 years neighbors model here. I highly encourage you to swap whatever model you feel like with other features that you think are interesting and you want to investigate. So what did I do here? So I used the very same scheme that I described earlier. Right here. Which is that I have an estimator, right? In this case, it's k-nearest neighbors. Now I have some features which I have in my mind I hypothesize are useful, which will tell me something about when the interview time is. I'm going to ask a question. 30 seconds has elapsed. How much longer to go? So what I did, I did this very same thing. I took my entire training set and I turned it into a bunch of randomly selected smaller data sets. For each one of those smaller ones, I trained my model. So in isolation of the other data sets. And then for the resulting model, I asked it that question. 30 seconds, what's your best guess? This results in as many values as I had training sets, right? And in this resulting number of values, I can directly evaluate what is the 99% confidence interval. And that gives me the knowledge of how can I compare that to what it was initially. Did it get smaller? Did it get smaller? Where did it get smaller? Or did it get larger? Or didn't do anything? So let's find out. So I made 100 bootstrapped data sets. For each one of those, I'm going to train this model. Now, get some predictions. Let's get some error bars. See what happens. All right, so in this case, what did we do? So we looked at X value. X value is the elapsed time. I fixed, so 1000, this is the next feature which I paid attention to, which is the how long it has been since one of his friends mentioned him. So in this case, I just fixed that in 1000 seconds. It's been 1000 seconds since someone mentioned him. And then this is the third feature, which was tweet length. And so I'm just shooting that to be some random number between 0 and 104. So previously, right, in the previous part we looked at, all of these things were random. We didn't know about any of these variables. We were just looking at how long has it been. So now we're adding knowledge of these other two, and we're going to fix the value of one of them. And so if the hypothesis was right, fixing this value will have an impact. So here is the resulting confidence value, or 95% confidence value, for a whole bunch of points, right? So 0 seconds have elapsed, 20 seconds have elapsed, 40, and so on. And you can see, still giant spread. Now, what if I change this to 100 seconds have elapsed since someone had mentioned it? What happens? Big difference, right? There's a part of the graph after 40 seconds has left where there's a lot of uncertainty, but it completely dramatically changes after a certain amount of time it works. Does anyone have a thought about why that is? Yes, sir.
Checks his Twitter every certain interval.
That's an interesting hypothesis. So actually, if you were to do a serious controlled study about this, you would have to account for how often does this person check. But the answer is no. That corresponds to basically a mention interval. And it means that the uncertainty in how long it was until he then responded, given that that was how long it was since he had been tweeted at, the uncertainty was extremely small. So this corresponds essentially to mention. So let's change that again to 10 seconds. You can see the uncertainty shrinks again. So in this case, we were in fact able to use knowledge of a couple of features to change our uncertainty.
So what you're showing here is that you're able to accurately predict it. Is that what that was
Yep.
showing without? So you're able to know?
Only in
graph
certain
showing?
places. Only in certain places.
Okay.
So the result of this is that if you are close to a spot in which, so what I was trying to illustrate there is as the distance away from a mention increases, your uncertainty increases. But if you are close to the spot in which she was at mention, the uncertainty becomes very small, becomes absolutely minuscule.
Oh, okay.
So basically that says, if I know how long it's been since this person, if I'm within this small neighborhood of when this person was at mention, I can tell you with great certainty when he's going to be next. And so that's what you can tell your boss, for example. And he says like, okay, I want the knowledge of when this person is going to say something. This is a very influential person. I want to know when he's going to say something. You can say, well, I can tell you the answer only at these moments. And that's when I'm able to give you an answer that means something. Outside of that time, any prediction that I can give you is not useful. It basically has this massive amount of uncertainty.
So with that other graph where it was showing like after 40 seconds, and it sort of was, there was no confidence interval, that means after 40 seconds you were able to accurately determine when he was going to...
At
that moment.
Yeah. Prior to then, it was the data didn't support saying. Okay, so we're at the very end of the lecture material. So I just wanted to summarize all the stuff that I mentioned, which is thinking about uncertainty is very important. Hopefully I persuaded you. So just telling people an answer is not useful. It's important to think about what is the uncertainty that accompanies that answer, and what are things which influence that uncertainty. So here, we saw two things which are important to influence it, right? One is the amount of data that you have, but also features and unmodeled features, and why it's important to think about what features are influencing the phenomenon, and what is a good way to do it. We talked about conveying that uncertainty using confidence bounds, and a really good way to arrive at those confidence bounds is through bootstrapped data sets. There is a lot of theory about how to analytically arrive at confidence intervals, and it's very, very useful. There are whole books that are just on inequalities and statistics, and I think they're a good time. But using bootstrapped intervals is a very, very, very efficient way to shortcut to all of that. And lastly, correlation is extremely important, but I recommend that you add information gain to your box of tools for trying to understand the relationship between two variables. So hopefully that was enjoyable. Feel free to contact me at Dini, Dini@AT&T.com. So we're going to take a break for some teams, make some friends, and get together and work on the project. So see you in 30 minutes. Like people's names. You get rid of names and you do a symbol replace with like some nonsensical string of letters and numbers to do the symbol there, but it's consistently placed there. And you know location points at the time in which they were at that location. If you get a random selection of a handful of points, like 4 approximately points, in a 24-hour period, that was enough to uniquely identify the person. So just swapping out the name wasn't enough. So the question is, what is enough? So if you aggregate people into buckets, that really didn't help. If you added noise, that definitely helps. It increases the number of data points that are required in order to uniquely identify a person, but it doesn't eliminate the possibility. So it turns out this is a very challenging problem which is ongoing. But what's interesting is that this very same phenomenon exists in multiple mediums. So one is location data. Another is sales data. So I think it was the same group that did a study of the very same phenomenon over sales transaction journeys. So if I didn't know your name, I simply had some unique symbol, and I knew what you bought, and or I knew what you bought, what store it was from, how much was the transaction. That was enough to uniquely identify people with a very small handful of points. And if you start removing things, so if you remove things like the amounts that they paid for stuff, you simply knew like where they went and what time they went there approximately, like what store and like what time of the transaction. This was essentially it. And so identity is a big deal. It's something that AT&T paid huge amount of attention to. One of the first things that I worked on when I got there was how do we anonymize data? How do we make it hard to identify? And what I would like for you to do is to investigate the degree to which that exists in Twitter. So let's suppose you don't know the name of someone. Is it possible, what is the degree to which it is possible to uniquely identify a person based upon features in that data? And then how can you alter that to then make that person harder to identify? So you have 3 data sets. The tweets from John Gruber, Mark Arment, and John Syracuse. So the way that I would suggest that you proceed is, so you have a labeled data set. So you can characterize the problem essentially as, here's a tweet. I want to classify who does this tweet belong to. And this essentially gives you a labeled data set. You can examine which features, based on features that you think are important, which features have a strong influencing factor over this label of who it belongs to. And then you can mess with that data, maybe injecting noise, maybe changing it according to some systematic way, and then observe how accurate of a classifier can you produce after injecting that noise. So if you were to just run the same, train the very same classifier on the same data set after altering it, can you illustrate that that has an impact on making it harder to identify? So that's essentially the problem. So I would recommend you get together with some teammates, start working on the problem, and I will come around to you and see how you're doing. And you've got an hour. Go for it. Yeah. So the data for this problem is in the link that I put up on Twitter. So if you go to my first screen, the data is there. So it's the 3 JSON files. You guys both have the data?
Yeah, we do.
Okay. 1, 2, and 3. That's right. Okay, so
you leave it down. And then
So here's the problem. So you got to. You guys want to? I chose the maximally suboptimal position. So you got a bunch of tweets, right? T1, T2,
Yeah, and each one, you have their labels, right? So you know which corresponds. So you could split this up and you could train a classifier, right? But you have to decide what features go into the classifier, right? So let's suppose, you know, what's a feature that's reasonable to hypothesize, right? Tweet length, I'm sorry?
The hashtag is?
Yeah, sounds reasonable. Hashtag? Yeah.
How do you move something to others nodes?
Oh, like sentiment?
Sentiment.
Sure, okay. You could use that, but it's a little bit more challenging because like it has to go through a processing step. So I would propose using things that are easily extracted. So
You said we have.
so such as length. You could look at things like what's the average time until it eats next. So like to capture some notion of like if you eat a lot, the day is small enough.
Time of day.
Time of day, absolutely. Yeah. So like, are they?
Getting it scheduled.
Yeah, exactly. Are they waiting at a train?
Yeah.
That's when they turn out to. That's when they see. So these are all very easy examples. So what I would propose doing is I would look at these in turn for some formulation, right? So maybe you wouldn't want to look at straight like date timestamp. So if you look in the iPython notebook that I have there, I bin this into core value by morning, date, and so you can ask the question, does the value of this variable strongly influence the value of the person that was assigned to it? Right? And so maybe the outcome of that will be, like sentiment would by far be the thing that has the biggest influence. And so that gives you the knowledge, okay, if I mess with sentiment, maybe that will make it harder to identify this. Does that make sense?
Yes.
What tool should we use
Right. Yeah, I think so.
Well, so in order to answer that question, let's think about what are the tasks that are involved, right? So there's two things we want to do, right? We want to classify it, so we have some manner of classifier. Secondly, we want to measure what is the relationship of this variable of one of these features to the variable. And so the way that you do that, so one way in which you do that would be information gain that we talked about earlier today. You can also use covariance, which is the conventional method for evaluating this. And that's just whatever tool you would like. So like NumPy, for example, has a covariance tool. Information gain that really isn't a really good tool, but I included one in the package which you can use, and examples of usage of it are in iPython. Go for it. Okay. Make haste.
You don't think it's classified?
Or should we do that?
Yeah.
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 Oh, yeah.
Yeah.
It's just a format.
I'm sure it's going to be. I think this
How does it do that?
I don't know.
So that would be
We are also trying to figure that out.
Throw that if you want to.
Okay. This is a chicken. And it comes with Amazon. So you have Amazon. So you just you would just go to your yeah, so pull up the command line and you so it gives you and something you might have to do it here, so you right click, and but you just right click here, and click on command prompt, and this will pop up. So make one pop up, and you just, and then in your directory, this is everything right here, but you just type Python, space, no, and it'll pop it up in your browser.
You know what? I like because the terminal that you don't have to like you just open it just like a normal file. And it's in my download folder.
That's one of the
You can comment it out if you want. That hashtag and put it in, and then when you run whatever, it will be recorded. And that way it's still there if you want to, or you can just leave it here and just space it on. Okay, yeah.
Oh, it needs
Is that what you're trying to do?
Yeah, I was trying to see how I can do it like this.
Oh, yeah. You can remove some.
But it only goes
Oh, you can probably, yeah, I think you highlight them all. You have to hold it down to. Oh, you're hitting shift, not control, that's exactly why. Now click the next one.
it's this part. Put it into a variable and then sort on it. So take a hashtag out and then sort on it. It says it can't go in place. So just put it into a variable.
60s. He's like in his 70s, so I'm easy to find on the internet. Yeah, thank you guys very much. And I'll also be speaking at the conference in November. So I'm going to be giving a talk on AI and machine learning and sort of how they're separate things but mutually support each other, and sort of this business about planning and long-term reasoning and sort of how this works with machine learning, and they go hand in hand to do interesting things. So if you want to hear about that, you can come see that. Thank you guys very much. If you have any comments, please feel free to direct them to Hi or Hannah. But it's been a great pleasure. Thank you.
Just a couple more words. So we have this space until 5 p.m. If you want to stick around a little bit, around 4:45 or so, we want to probably start migrating people out. But yeah, thank you so much to all our fantastic volunteers today, to Gabriella for giving the morning presentation, for Don for this fantastic workshop. Can we have one more round of applause for Don, please? And yeah, we'll see you in the morning or tomorrow afternoon, or the workshops on Monday or Tuesday, and of course the conference. So thank you all for coming.